So, in general expression for the stability factor, we have derived stability factor SF equal to 1 plus SF equal to 1 plus beta divided by 1 minus beta dIB by DIC. So, this is your general expression for the stability factor. So, this expression relates the particular biasing method is suitable or not. If the value of the stability factor is less, the stability is more. From this expression, if the value of the stability factor, value of the stability factor SF is less, the stability will be more. The stability will be more. Stability will be more and vice versa, more and vice versa. If the value of the stability factor is more, then stability will be less. If the value of the stability factor is less, the stability will be more. If the value of the stability factor is more, the stability will be less. That is, Q point IC and Vc should be independent of the variation of the transistor parameter, that is IC, beta and Vb. So, then biasing methods. Biasing methods. In a transistor biasing, there are 4 biasing methods. First, number 1 is fixed bias, fixed bias. Number 2, that is your feedback bias, or alternative name is your collector to base bias, Third one is your emitter bias or self bias, emitter bias, and fourth one, that is your voltage divider bias, There are 4 biasing methods as far as transistor biasing is concerned, that is your fixed bias, feedback bias, emitter bias and voltage divider bias. We will go through one by one and analyzing these biasing methods and related with your stability factor. If the stability factor particular biasing, we have to analyze that biasing method is suitable for transistor biasing or not. Now, let us go through one by one. First, fixed biasing methods. Fixed biasing. Fixed bias. So, this is your fixed bias configuration. This is your a common emitter transistor and there are 2 resistance RB and RC, and there is your supply voltage, that is your VCC, collector supply voltage, and this is your grounded, and this part is your base, this is your emitter and this is your collector. This is your fixed bias method. In fixed bias method, I can simplify this circuit so that it will be easy for you. So, this is your plus VCC, remember this is your plus VCC supplied with both input loop and output loop. The VCC is supplied both input and output. If I will simplify this circuit, this will be like this. This is your RB, this is your RC, this is your let VCC here, this is grounded VCC, and also this is nothing but your VCC, this is grounded. the simplified model of fixed biasing method. This is your RB, VCC is supplied both RB, here this is your input, the current flow in like this loop, and this same VCC is applied in the output loop. This is your input loop and this is your output loop. Then what we will do? Apply Kirchhoff's voltage law to the input. We have to calculate base current IB, collector current IC, then we will go to the stability factor SF 1 plus beta by 1 minus beta dIB by DIC. In a fixed bias scheme and the same VCC collector supply voltage is supplied both input, means this is your base emitter loop, and same VCC is supplied collector emitter loop. I have simplified this model. This one, this is your, look at this, this resistor is connected to the base, this is your base, this is your emitter and this is your collector. Already I told you there are 3 current, base current, emitter current and collector current. Since this terminal is connected to the base, generally the current flow through this is your base current IB. Since this terminal is connected to a collector, the current flow is nothing but what? Collector current IC. The resistance here, the current flow is IB, here there is a resistance RC, the current flow is RC. Only 2 resistance present in fixed biasing scheme. So, another important thing is, if there is a base and emitter, always there is a potential between base and emitter, that is your VB. You should consider the base emitter voltage, it is very very important. If there is a transistor between base and emitter, there is a potential, that is your VB, you should take, consider this VB. Between base and emitter there is a potential VB. Similarly, between collector and emitter there is a potential, that is your VC. Okay? Our circuit is completed. This is a simplified model. I have simplified this model from this your fixed bias scheme. Then I am applying Kirchhoff's voltage law to the input loop. Apply Kirchhoff's voltage law, apply KVL Kirchhoff's voltage law to the input, apply Kirchhoff's voltage law to the input. Already I told you what is KVL. Algebraic sum of the potential in a closed loop is 0. Algebraic sum of the potential in a closed loop V equal to 0, summation of V equal to 0. If there is a voltage, keep as it is. If there is a resistance, multiply with the current. If there is a resistance RB here, the current mentioning I have already mentioned, that is your base current IB. The direction of voltage source, if you move from plus to minus, that is minus, minus to plus is plus. Here the current is flowing in like this direction. So, current entering this resistor, this terminal is plus and leaving that is minus, current flow in this manner. So, entering plus, leaving minus, and there is a potential VB. If you are applying KVL to the input loop, what is my equation? Here minus to plus is plus, that is your VCC, again plus to minus, minus IB into RB, IB into RB, then plus to minus, minus, that is your VBE equal to 0. It is very very important. This is your equation 1. In this fixed bias scheme or any biasing method, there are 2 loops, one is your input loop, another one is your output loop. Apply KVL to the input loop, you will get the input equation. From this input equation, find the input current is your base current IB. My intention is apply KVL to the input loop and find the input current is your base current IB. So, from this equation I will calculate the value of IB. So, this is your VCC minus VB equal to IB RB, or IB equal to how much? VCC minus VBE divided by RB. This is the expression for the base current in fixed bias configuration. In fixed bias configuration, if you apply the KVL to the input loop, you will get this the input current is your base current IB, the value will be VCC minus VB by RB. Similarly, apply Kirchhoff's voltage law to the output, apply KVL to the output, tell me if you move from plus to minus to plus plus, plus to minus minus. Here minus plus terminal, this is your minus terminal, the DC source, If you move from here in anticlockwise, minus to plus plus VCC, there is no resistance here, there is a resistance, current flow in this anticlockwise direction, current entering this resistor at the entering point plus and leaving, that is your minus. I am considering in the anticlockwise direction, that means this one, algebraic sum of the potential in a closed loop 0. So, this is your, there is no same potential, minus to plus plus VCC, again plus to minus minus, the collector in this resistor the current flow is IC. So, here plus to minus minus IC into RC, then you should consider this one potential collector emitter, that is your VCE, minus VCE equal to 0. Again, if I will apply KVL to the output loop, what is my output equation? Minus to plus plus VCC, plus to minus minus IC into RC, plus to minus minus VCE equal to 0. So, that is your VCC, then minus IC into RC minus VCE equal to 0. This is the output equation. If I will apply KVL to the input loop, I will get the input current is your base current IB equal to VCC minus VB by RB. If I will apply KVL to the output loop, I will get the output current, that is your IC, VCC minus ICRC minus VC equal to 0, or VCE equal to VCC minus ICRC. So, this is your output equation, this is your equation 1 and this is your equation 2. So, in a fixed biasing scheme, how to find the Q point? Q point means IC and VC. If you apply KVL to the input loop, you will get the input current is your base current IB. Once getting IB, then you can calculate IC, because IC equal to beta IB, one of the operating point you can find out. Then if you apply KVL to the output loop, this is your output equation, you will get the VC. So, in this way you can find out the operating point IC and VC. So, next, that is your stability factor. So, we will analyze the biasing scheme is suitable or not, but with the help of the stability factor expression. In a stability factor expression, in a stability factor expression, we know SF equal value is how much? 1 plus beta divided by 1 minus beta dIB by DIC. Remember, the beta value is fixed. Any transistor beta value is always given. Only the variable is this one, dIB by DIC. How to get the dIB by DIC? Apply KVL to the input loop, you will get the input equation. If you will differentiate this equation with respect to IC, then you will get the dIB by DIC, and substitute these values, and then you will get the stability factor SF. Here IB equal to VCC minus VB by RB. If you are differentiating this equation, this is your, if you are differentiating this equation, then what will get? VCC is a constant, 10 volt, 20 volt, 30 volt DC voltage given, any derivative of any constant term is 0. VB is also constant, 0.3, 0.7, 0.3 for germanium and 0.7 for silicon, and this VCC is a constant and VB is also constant, and the resistor RB is also constant, the value is given. So, this whole term is constant. So, dIB by DIC will be 0. If you will differentiate this equation, then dIB by DIC will be 0. So, dIB by DIC, if we will differentiating equation, this equation star, so dIB by DIC equal to 0. If dIB by DIC equal to 0, what will be your stability factor? If you will substituting SF value is how much? That is your 1 plus beta by 1 minus 0. So, ultimately this is your 1 plus beta. So, stability is improved or not? The stability is not improved in this biasing scheme, because the beta value is given and SF if beta value 50 or 100, the stability factor may be your 51 or 101 like this. The stability factor is not decreasing. If the stability value decreases, the stability will be improved. So, that means particularly this fixed biasing scheme is not suitable for biasing purpose. Thank you.